Well, g'day flatties and globe defenders. This is Critical Think from Down Under. Thank you. Yes, it's been a while and you can see I'm coming to you from my Thailand studio today. And you know this because I'm up the right way, because if I was in Australia, I'd be upside down, right? And I'm sort of like having to come out of temporary retirement because I'm having a few discussions with a flatty friend of mine, and I'm needing to put together some material to try to explain some of the globe concepts. And I thought doing a video would be the best way because visualization to me is a good way to explain something. The topic I'm going to discuss today is one that is chronically misunderstood by flat earthers, and that's about the horizon and the lateral curve, or lack thereof. Now, one of the prime precepts of flat earthers is NASA lies, therefore Earth flat. No, this is just not the case. The fact of whether NASA lies or not has no effect on the shape of the Earth. It cannot turn flat into globe or globe into flat, right? Let's just say NASA's making everything up and all the space journeys are CGI and all that. Let's just pretend for a moment that's true. But how does that change the shape of the Earth? I don't know. NASA cannot stop me from going out and looking and observing and measuring, and through my own intelligence and training and engineering and math skills, work out what the shape of the Earth is. NASA can't alter that. So it doesn't matter if NASA lies or not. They can't change the shape of the Earth that I can measure. The other thing I get all the time, it's very boring. I can't see the curve, therefore Earth flat. Now, this is due to a misunderstanding of what you're looking at, a misunderstanding of the globe geometry, and a misunderstanding of the scale of the globe. Now, the Earth is pretty big, and you're not always going to see a curve when you look, especially when you look side to side. So I've discovered that part of this misunderstanding is this statement: a sphere curves at the same rate over its entire surface. Well, you might be surprised that I've buzzed that one, but it's only true for great circle lines. And great circle lines are the ones that if you were to use a knife to cut your sphere, they would cut it in half. There are many other curved lines on a sphere, and they're not all the same curvature as the great circle line. And this here is one of the key things to understanding why flat earthers insist on seeing side-to-side curvature when their geometry insists that you can't notice any curvature from the height that you're trying to view it from. So this is what we hear. If the Earth curves away looking straight ahead, it should also have the same lateral curve. A common thing that flat earthers say. Well, actually, yes, it does. If you're looking at the horizon some direction, just rotate 90 degrees and look again. It will have the same lateral curve. So I don't have a problem with this statement as such. It's just that flat earthers cannot interpret it correctly. They think it means something different. So if I'm looking to the left at the horizon, say 45 degrees, the Earth curves away. If a ship was to go away from it, it will go over the curve. And if I change 90 degrees to the right, which is a lateral attitude to where I was before, then the ship is also, if you were to follow a ship, it would also go over the curve at the same rate. So the Earth does have the same lateral curve as it does out, but that only applies to where you're standing. It does not apply to the horizon. Here's where that previous statement, it is true, gets confused with translating into reality. If the Earth curves away looking straight ahead, I should also see the same lateral curve when looking at the horizon. No, that's not quite right. In fact, not right at all when you consider the geometry of a globe. And I will be demonstrating all these things soon. Now, I have never been a fan of using lateral horizon observations as a method of determining curvature. There are far, far better ways and less error-prone ways of measuring curvature. You're always going to get into silly little arguments. So a far better and less error-prone way is measuring horizon drop. Just consider this, like the Earth is 70% covered with water. Now I'm in the desert and I see no water. Now the problem is I should not expect to see any water in the desert. And it's the same thing with horizon curvature. You should not expect to see any horizon curvature when you're close to the surface of the Earth. Now, in my experience, flat Earth believers are 2D thinkers. They have difficulty comprehending 3D space. And so we end up with they're straw-manning the globe. They don't understand what the globe should present in reality. And then they say, oh, I don't see it, therefore the Earth is not a globe. The other thing I get is horizon drop is caused by perspective. Now there's no known mechanism in which perspective might cause the horizon to drop. I've asked for such an explanation many times, never received it. I'm going to demonstrate here today. It just doesn't seem to hold when you look critically at perspective. So the other thing I get, just as an aside, that this here is a picture of a ship with the bottom cut off, and this is due to perspective, of course, or should I say perspective, the magic version of perspective. So what we see here, is this also due to perspective, or is this just someone going over a curve? We often hear flatties dismiss all these tools we use to help determine what our reality should look like. So a model, diagram or CGI is not reality. So what a flatty will say is, these things are not reality, therefore you can't use them as evidence of the globe. No, you can't use them as evidence, but you can use them to check against reality. The use of modelling for the purpose of a hypothesis generation or education is scientifically sound. A model is not reality, but it will make predictions what reality is expected to look like. The validity of a model can be determined by observing reality to see if the predictions are correct. So, for example, in the flat Earth model, the Earth is flat. So this comes with it a certain geometry. Now, in this geometry, you can make predictions. One of the most obvious predictions is that when you look out to the horizon, the surface of a flat plane will appear to rise to eye level. Now, if you come across a situation where that is not correct, then your model is not correct. This would be why flat earthers hate such observations of horizon drop, because of course it disproves the flat earth model. I've built this model in Blender to help visualize and discuss the differences between flat and globe and what you should be looking for as a good test of if something is flat or spherical. Now this is the flat plane version. I'll try to explain some of the things in here. This Stonehenge type structure, I built it just for reference. It's not meant to convey anything in our known reality. It's just an arbitrary structure that helps you to visualize what I'm trying to explain here. So this is a flat plane on a scale, it's all about 12,000 kilometres to the horizon, and the eye level would represent about 10 kilometres in this scale model here. Now there's a few features of here. The top screen is my user view. It's in perspective view. So if you're wondering what perspective should do, then this modeling tool is constructed such that it follows the rules of perspective, so you can easily visualize how perspective works. In the bottom half of the screen, I've got a camera mounted. The view from the camera, which is 10K up in the air on this scale model, and this window in the middle of that there is the viewport. On either side you'll see some of my columns, and they appear slanted, the ones on the side. This is an effect of perspective. So if you look at this viewport of the camera, that's what you'd be looking at if you took a picture. In this case it's a 50mm lens. Now around this yellow circle around the Stonehenge is the eye level. You'll see that circle in here. The eye level is that yellowy orange line there, and I've got two flat pieces that go off into the distance, and obviously due to the perspective they remain straight lines and they appear to converge. So looking at this, what we all know about flat surfaces, the horizon rises to eye level. So I'll just zoom in a bit here. So this here, I've got the lighting turned on from above, so you can see the shadow of this ring I've got on the top of my Stonehenge thing, and it's shining a shadow on the flat plane, and you can see the shadow under the eye level. And so when you're looking in the camera view here, you can see a little bit of that shadow of the ring there. Not so easy to see the eye level one because it's further away, but an important thing you need to understand about flat is that I can see beyond that ring, and I can see all the surface up to looks like it's right up to the 12 kilometers away. Of course it gets compressed in the distance, but I haven't drawn grid lines on this. So here's the shadow here. I can see for many kilometers after that shadow. So that's the flat Earth. The thing, if you're wondering whether your surface is flat or not, you'd be looking for these couple of things. Can I see the surface out to a very long way? And does the surface rise to eye level? And this is not eye level as you point the camera, but eye level as measured using a proper instrument. So a lot of people will say that eye level is basically where you point the camera, which is obviously a load of rubbish, and you need a measuring instrument to measure the eye level. This measuring instrument could be a water level, an auto level, or a theodolite, for example. Now I'm going to take this flat Earth and move it out of the way. So here's my globe model, which I've taken the flat plane away, and this is underneath. It's only the top part of the globe, not the whole globe. We don't need the whole globe. So all I've done is I've just taken the flat plane away. These two planks of perspective are still here, and I've still got my camera view there, and in this view you can see the green plank to the left and the woody coloured one to the right. Just going to move my camera up a bit so that you get a better view. I'll explain everything in the picture shortly, but for now I just want to explain this here is the globe horizon down the bottom. This here are the perspective lines, just the same way they were on the flat earth. And so immediately we see that the horizon is way below eye level. The eye level line is still up here. So the perspective did not make that horizon drop. This perspective left those straight pieces up there in their place, and nor should you expect that perspective would make them drop. That's just not possible. So the argument that perspective can cause a horizon drop is pretty ridiculous, especially when you consider that if you're looking out from a globe and the surface curves away from you, always curving away, then of course the horizon is going to drop. I mean, this is pretty simple, but if you had trouble believing it before, this is evident in this model. Now I'm going to explain some of the other things in this picture, but first I'll take the perspective lines away. Right, I have this blue and purple cross. My observation point is in the middle of this circle. The blue and the purple lines are great circle lines. One is lateral and one is straight ahead. And you can look one way, look the other, and you will see the same curve away. Now, when you're looking at the horizon will drop the same in every direction. So no matter which way you look, the curve is the same. Remember, the sphere has the same great circle curves in every direction. So the horizon is curving away in every direction. And so if I rotate the camera here, so this is not a real-time renderer, this is just Blender, it's creating models, so it takes a little bit of time for the renderer to catch up. But if I rotate my camera, then the horizon is always at the same spot relative to your elevation. And this is perfectly understandable because, yes, there is a little bit of a hump in the middle and you're looking down, but you will see a horizon because the surface is curving away from you. And so as we rotate around, I'm not sure why flat earthers expect to see this horizon horizon dipping as you turn around. I mean, it's the same drop in every direction. Fundamental geometric fact. Now the other thing is this red line here is just say I'm looking out at the horizon, and this red curve represents the path a ship might take as it travels around the curve. Now this is not a great circle line, and so it is at a different curve to the great circle line. So if I click on that object and look at the modifier, it's got a curve of 36.8 degrees. Where I look at this other one, it's 40.6 degrees. So no, it's not the same curve for a start. And the other thing is, this blender model is not perfect because a sphere is made up of segments. So you will see things like this. And to correct that would take a lot more work that I'm not prepared to do right now. I'm illustrating a concept, I'm not getting it perfect. Now I know that a lot of the flatties will argue that because it's not perfect, it's not a sphere, that you can do that if you like, but everyone else who have eyes can see that it's a sphere and that these are imperfections. So if you were to observe a ship from your observation point, you're looking at this ship. The highest point that the ship would be is at perpendicular, right? This ship is going across your line of sight. So when you look out in direction perpendicular to the path of the ship, this is your highest point. It only makes sense because the sphere curves away to either side. This point is below this point. So I'm looking at the ship here. When the ship goes this direction, this is the highest point and it will only go down from there. The other thing is that, come back. When flatties are looking at the horizon, they are expecting to see a curve like this, when in fact the problem is the horizon will block that curve. And if we look at this from the camera here and we see the ship, and then we come to a point where that ship dips over the horizon and you don't see it. Again, I'd say this is not perfect, it's not entirely accurate, and to get it entirely accurate would require you wouldn't be able to look at this in real time because it wouldn't be able to render it quick enough. So maybe a project for the future that I'm sure that may be able to transfer this to a real-time rendering engine like Unreal, and it could work a lot better. So right now I'm sure that's going to be a stumbling block for many flatties, but just look at the concept and what I'm trying to say here. Your line of sight is blocked from that curved path. All you see is the horizon, and the horizon is flat around you. It's like a hula hoop around you. And that's like I've drawn this hoop at the top of my Stonehenge. So when you're looking at that, you're only in a very small bump above that horizon. Then it will be like looking at a hula hoop side on. So I've got another camera that's inside the top there. So if you're very close to the horizon and you're looking out, you're going to see, if you hold a hula hoop sideways, horizontal, like this hula hoop is horizontal, if you're inside the circle and not very much height, you're not going to see the whole curve of the hula hoop. You're just going to see the smallest one. In fact, almost none at all. And the actual geometry of that curve you will see means that it is so small that you cannot resolve it with a camera close to the surface. The lens distortion and whatever other things will outweigh whatever curve there is. It'll be less than 1 pixel on most cameras. So maybe you are expecting to see this, but when you're down there, you're only seeing this. You're seeing flatness, and a lot of flatties will see that and say the Earth's flat. So I'll switch back to the other camera view. So what I'm trying to say here with this red curve, if that's like the top of a ship sailing to the side of me, eventually it will follow the curve and go over the horizon. This is just the geometry of the sphere. And the horizon is not the same curvature as that red band. The other difference is very, very easy to measure, is that the horizon drop, it's easy to see, easy to measure, and that's a better test of curvature because you know the horizon is going to drop because the surface is curving away from you the further it goes. So the horizon drop is really a no-brainer. The other difference with a flat Earth, you can see beyond this horizon. If the Earth were flat, there would be no horizon. You would just keep seeing for many, many, many kilometers. And as you can see here, once you reach the horizon, the Earth is curving away beyond that. You don't see the surface anymore. So there's two things to look at if you're trying to determine if the surface you're standing on is spherical or flat. And the lateral curve is not one of those things that will give you a good enough resolution, a good enough measurement. But of course, I understand perfectly why flat earthers would cling to that, because it allows them to retain their faulty belief that if you were to look at the eye level and the horizon, look at things disappear over the curve, realize you cannot see the surface beyond a certain distance, then these things you can use to test whether the surface you're on is ever so slightly curved or flat out for several thousand kilometers. That's probably dealt with most things. But there was something here I noticed. I'm not sure what this is. Oh, let's have a look here. Oi, what's that? Oh my goodness. Oh, just a minute, I've got to try and get this in sight. Oh, bloody hell. What's that? How did NASA get that CubeSat into my model? What the bloody hell are you guys doing? I thought I told you to stay out of this. Now, it's going to spoil the whole thing. Next thing you know, the floodies will be saying, geometry's all fake. A sphere is exactly the same as a flat plane? Look what you've done. Oh, wait a minute. They're already saying that, aren't they? Oh, okay.